Today I will teach the lecture 5, the vibration calculation method for the MDOF system. Sorry for the late upload of the lecture 5 video. I hope you quite understand of the situation. And how you understand the previous lecture, we already introduced the model analysis method for the MDOF system. So a model analysis is just want you to know how to find the mode shape and the different period of the different mode. This is the first step of the calculation of the vibration result of the MDOF system. Today we will based on the model analysis result to introduce the method to calculate the displacement and the internal force of the MDOF system. So let's get to start. And the next page. This is PowerPoint already uploaded into Moodle system, so you can find it. I already upload the notes, teacher's notes also in the Moodle system. And so we start to describe this MDOF system. And we take the example of the frame structure. And each node we will have more than have the 3 degrees of freedom. But we can introduce the method to you to simplify this model to be MDOF system. So in general, for this model, for example, okay, for this model, each node has 3 DOFs. So we can count that this have 60 nodes. So actually, this system should have 48 degrees of freedom, but we can use we call it the flexibility matrix to transfer this matrix to be a single degree of freedom system, as like because this is free story, so we can transfer to be the free DOF system. Use this method. This simplification method is quite simple, but we need to do some static analysis for this frame structure, or even shear wall structure also okay. Next page. Actually, we need to apply some lateral for this system. At the first step, we apply the unit load, or the certain loading for the top floor. This coordinate we call it the number 1 node, or number 1 DOF. This is second, this is third. So we can know that when we apply the horizontal force at the top, this model we have the rigid floor diaphragm situation, and then we apply the loading at the top, so we can get 3-story displacement. So we mark as F11, F21, and F31. And the second situation, we apply the unit force at the second floor. So we mark the F12, F22, and F32. This is free displacement for the 3 nodes. So flexibility matrix is let you to get the displacement. So we apply the unit force, and then we can get the displacement. So it compared to the matrix, the stiffness matrix is different. Stiffness matrix is apply the displacement, and then you get the reaction force. But for this one, we just apply the force, and then we get the displacement. So after we get these 3 displacement, then we can use these several displacement data to form the stiffness matrix here, and then we just reverse the matrix, the stiffness matrix, the flexibility matrix to be the stiffness matrix. So it's K equal to the F minus 1. So this is the metric calculation. Just reverse the metric, it's okay. And then after this step, we can get the matrix. But for the idealized structural property matrix, we know that this is the shear model, or we call it the simple MDOF system. So we can use K1, K2, K3 to show this matrix. we already described in the previous lecture. And this is the mass matrix. And this is the external force. In this example, we use V. In the previous lecture, we use P. And this is the displacement, the 3, 4. So we focus on the basic equation already described in the previous lecture. In this, use the MDOF system, we can compute the model result for this MDOF system. Model result means two things. One is the mole shape factor, or you call it the mole shape displacement, and the each mole's frequency, circular frequency, or we call it the period, or each mole. We also can get from the model analysis. So the model analysis we already described in the previous lecture, so we just don't have more detail for this one. And we know that each displacement, for example, we already have the model analysis. We know that this 3 DOF system, we have 3 mole shape: first mole, second mole, and the third mole. And then no more, because only 3 mole for 3 DOF system. And we know that the displacement, not displacement like each node, for example, like this, several nodes. The displacement, we have 2 methods to describe this displacement. We can use the coordinate displacement. For example, this is 0.3, 0.2, and 0.1. Each node had the horizontal displacement, so we can describe the displacement for the real time. But we also can use another method to describe the displacement. We use the mole shape coordinate. For example, we can use displacement like we use the vector. For example, the u1 vector by this mole shape. So the mole shape is phi 1, phi 2, and phi 3. And plus u2 is a vector by the second mole. 1, no, 3. This is the second mole, this is first mole. And the third one also, we just can supervision these 3 different mole shape to describe the final displacement. So we can use this equation to describe each node of the displacement. Each vertical one, this one is the mole shape, and this one we call it the model coordinate amplifier of the mole shape. So we can use this one to describe each node's displacement. So this is the assumption for the model supervision method. Second part, we just need to use the mole shape vector to transfer every single element in the basic equation, like a mass, stiffness K, damping C, and the external force PT or VT. We can use the mole shape to describe each of the element, but we just call it the generalized mass, generalized stiffness, generalized damping, and generalized force. So after we use this basic assumption, we can change this basic equation. This is the basic dynamic equation. Use this assumption, every displacement can use model coordinate to describe, and we put back this equation back to the basic equation, and then we can find this equation. Each element we multiply by the phi t. Phi t means the phi matrix rotate, and then we put it back, and then we have this equation. So that we just called previously, we just called this element after multiple by the phi t and the phi, we call it the generalized mass. This matrix is generalized mass, generalized damping, and generalized stiffness, and the generalized external load. So we can transfer to be this basic equation to be the 3 different mode basic equation. So very easy is that we can transfer. Actually, we have the basic equation for each node. So we have the basic equation like m U, this is the matrix, and the Cu, this is the velocity, and the Ku stiffness and the displacement equal to Pt or Vt. And this is basic equations for each node. We can divide this equation to be each mole's equation. But each mole we have certain different mass for each mole, different temperature for each mole, and the different stiffness for each mole. So this different basic element for the equation, we call it the generalized mass, generalized temperature, and the generalized stiffness. And finally, we equal to the generalized external load. So we can transfer this equation to be, you can see that the form is m, so we put the m to the here, minus m, each one minus m, and use the lecture 2 basic equation, damping ratio equal to the C constant minus 2m omega. Use this basic equation for each mole shape. We can finally find the basic equation for the different mole. For the first mole, we had this is the mole 1 acceleration, mole 1 velocity, and the mole 1 displacement. This is the damping ratio for the mole 1. So for the normal case, the damping ratio for each mole is almost the same. So for example, the system damping ratio is equal to 0.05. So every mole is equal to the same value for the mole, for the damping ratio. And the omega 1, it means for the mole 1's omega 1. This is for different mole, the value is different. And this is velocity, and this is the mole omega 1 square. Why is square? Because we use the equation, because in this matrix we just use k minus m, so we use omega to describe this value. So you can use omega 1 square by the, so this is the reference to the k, this is used c, and this is used m, because already minus m, so we can use this basic equation to transform. Finally, we can get this one. And remember, this is the generalized external load, so we need to use the motion factor to generalize the external load. And this was minus the m1. We put the star, so it's the generalized mass, but the first element, the mass mole 1 element. So we can transfer in this equation. This is the basic equation for the mole supervision calculation method. So because this part is quite difficult to understand, so we put the real example digits to calculate. So in this process, so that you can know how to compute the vibration result from the using the model supervision method. In this real example, we can note that the coordinate, the MDOF coordinate is from the top to the bottom. So the top is the first degree of freedom, the second one, the third one. So it's K1, K2, and K3. The location is quite different as before. So be remind the relationship between the story and the degree of freedom. So in this example, the damping ratio is 5%, like a normal concrete for each mole. And we know that we apply the earthquake loading. So this is the ground motion. Ground motion is a ground motion is series of data. So in this calculation, after you compute every very important result, maybe can use Excel table to compute all the result, because it is a series data. And we know that the maximum acceleration is 0.535 g, so it means if g is 10, it's like 350 gal. 1 gal equal to 1 cm per second square. So this is the basic unit for the ground motion. We use gal. And so after we know that this is the, like in the United, we can transfer to be the general unit, and this one is the result. We can use turn or the KS square per inch. We also can understand as turn. It's almost the same. But remember, the G value is quite different in different unit system. But for easy understanding, we just call it turn. It's much more easy to understand. So latest the value is the mass for each floor: 1 ton, 1.5 ton, and 2 ton. And this is the stiffness, or if the turn, so the stiffness should be N per mm or km per 1 meter is the same. And this is the stiffness matrix. You can use the K1, K2, K3 to extract this matrix. So after we have the model analysis, we can compute the different mode shapes equation T and the period and the circular frequency, and we can get the mode shape displacement. And then finally we can, after normalize, we can get the mode shape displacement matrix. This is the this is the first mode, phi 1. This is second mode, phi 2. Third mode, phi 3. Keep the top element to be equal to be 1.0. Make your calculation much more easier. And you can use this program I developed, I show you in the previous lecture. You can use this program to compute the mode shape analysis. Because mode shape analysis is quite difficult, so you can use software to do this part. And this is the normalization for the modes. We use the top value equal to 1.0. And okay, we know that the result we display as the graphic. We know that the mode 1, the circular frequency equal to 4.5 second radian per second. So this is the unit for the circular frequency. We can transfer to the period. It's quite more easy to understand. It's 1.37 second. This is the first mode, second mode, and third mode. Okay, and after we get this result, this quite important result you can use in the next step, especially the circular frequency. And in the next step, we know that this is the circular frequency. T is not actually we are used in the next step. So the first step, we compute the generalized mass. This is the equation, the computation of the generalized mass. In this textbook example is quite simple, direct to get the result. So we can change to the hand calculation. So this is the result. How to compute it? We get the matrix. So in the first one, we need to rotate the matrix. So actually, the real matrix of the phi is 1.0, and 1.0 is in the first row, not the first column, because we need to rotate. So we rotate the matrix, so become the first column is 1.0. This is the rotate matrix by this is the mass, original mass matrix, not the generalized mass matrix. So the first DOF is 1 ton, 1.5 ton, and 2 ton. So we use this method to compute this matrix. So you know that how to compute the matrix multiple by matrix is quite easy to understand this process. So this two multiple, we can get this matrix. This is not rotation of the phi matrix. So we compute these two matrix, 3 by 3 matrix. We can get the 3 by 3 matrix. So after this calculation, we can get the generalized mass for the first DOF system. Fourth DOF, the generalized mass is 1.8 ton. We can transfer to right like this. We just capture the diagonal element for this matrix. This is generalized mass matrix calculation. So we can know that this is different mode mass for the different mode. Okay, second step, we need to compute the generalized external loading, or we call it PT or the VT. And because this we use the ground data motion, we know that after we apply the ground field or ground motion for this structure, it means the foundation, we will have the ground motion movement for this foundation, and then we capture the external load for each node. So we apply, because it is the ground motion, we have the interior force based on the mass, so we can have the minor effect. Minor m actually is if the acceleration is RA, this is the acceleration. So after we apply the A, we can get the reaction force called minor MA. So we can use this Newton law to generalize the external force should be equal to the minor m, but this m is not normal m, it's generalized m by the acceleration. So this is the acceleration. This is the acceleration record, and this is the minor is the reaction effect. So we compute the factor of the different external load. So we can get the in the textbook they get the direct answer for this one. We transfer to the Henkel for you to more easy understand. And this is the external load calculation. So in this equation, we know that we need to compute the mass first, generalized mass first. So we also use the rotation of the phi matrix. So this is the first column is equal to 1, 0. So we know that this is the rotation of the phi matrix. By the mass matrix, this is the mass matrix, original mass matrix. And by R mean, what's the R mean? R is the all the element is equal to 1.0. This is the unit vector. And then we compute, after we compute, we have find these 3 digits. This is external load, or call it the loading factor. External loading factor for the each different mode. This is not the actual loading, because we after this one we have multiple by the ground motion acceleration. We can understand the V equal to minor MA. This A is the acceleration. So acceleration is the series of data, not the certain digit or certain value. So after we compute the loading factor, we already know loading factor is the certain value by the acceleration. Okay, AT acceleration, or the minor, we can add the minor. And the previous one, because every element already over the m divide the m, so this is the temperature we already know, and this phi we use the mode 1 circular frequency, and this is the something we need to know, and this is the already used the mode 1 circular frequency. So in this equation, every single thing we already know. So we can write down the every single thing we already know. This is the computation by use 2 c omega. This is omega square, we already know. And this we already described before. You can see 1.425 is equal to this value minus m. So you can see in the next page. And then we know that this is, we already know the loading factor of the acceleration. So acceleration is a series of data. It's no matter, we already know in this part, because it's the, understand is the condition of this equation. And this series value we already know. So we need to compute the y1 and y2 and y3. How to compute it? And we already know that this 3 equation, and we how to compute this part. This part equal to the, already know that the MAT, generalized M, okay, and minus the M. This another M is the from the generalized mass. So in this calculation, we only compute the 2.50 like the previous part, like this one. And this one, we need to divide the mass. This mass is generalized mass. We capture from the mass calculation. You can see that this is generalized mass. So we can capture this part, and then we can compute the, oh sorry, this is VT minus M. So this is loading factor we already know, and this is the generalized mass. So we can use these two values to compute the 1.425. So we know that how to get the 1.425 by this equation. So after we get this equation, we know that this is what we already know from the Duhamel integration or any calculation method for the single degree of freedom vibration. This one is the single degree of freedom calculation basic equation. So in this calculation, we know that we just divide the MDOF system, like a 3DOF system, to be 3 single DOF systems calculation. It's quite directly derived from the using the modal analysis. So this is the modal participation factor we will describe later. And so in this equation we already described before, and we choose the mode 1 equation. This is the mode 1 equation. We put all the value we already know. This is the 1 because this is 1.0. We know that we can understand this part as the mass equal to 1.0. So we capture the single degree of freedom system. The shape of we need to know 3 things for this single of degree freedom system. One is the mass, the second one by the velocity, so we know that this is the damping constant, and this one is by the displacement, so this one should be stiffness. So we already know M, C, and K. So finally we need to know the external load. So this is the loading factor, and by the series of data. So in this equation, we already know the series data, or we already know in the condition. So we already know the mass, damping constant, and the stiffness and the external load. So this is the single degree of freedom system. So we can use the Duhamel integration method or Newmarket method, any method for the numerical calculation for the single degree of freedom system. But beware one thing, before you input any data in the program, we know that the external load you should multiply by the factor. For this one is 1.425. So after you put the external the time history data for the external load PT, you should multiply by this factor. So we need to scale up or scale down the ground motion to capture the real result. Or you can use another idea is to not to scale the data after, but it's also almost the same, but beware the step. So the better solution is you put this scale factor before the integration calculation. So you know that when we need to compute the 3DOF system, we just separate need to throw 3 by the single degree of freedom system. So each single degree of freedom system have their own mass, damping constant, and the stiffness. So you need to compute every result for the different motion. So this is the final result computed by the program or by Excel table, no matter what. But you can capture 3 result like this is, for example, after the calculation we can get the displacement. This is the basic result we need to know. So this is 3 displacement result for the different mode. This is mode 1, mode 2, and mode 3. each mode have different M and C and K, so the curve shape should be different. So if we need to know the result for each time step for the final result, so we have mode 1, mode 2, mode 3, and the third one is to the real structure of the final result, like certain a curve. So we know that this should be a curve. So we need to know, for example, we need to know the 2 second. What the result of the 2 second? So we need to capture every single result of the 2 second. This is the result from the first mode. This is the second mode here. This is the third mode, something like here. So we need to add up these three displacement results. So we call this method called the model super, or we call mode supervision method. Supervision means add up these three time history data together by different factor, of course. So what's the different factor? We can compute use this diagram. We know that after we compute, we know that the first mode is by the 0.3, second mode by the minus 0.676, and the third mode is multiple by the 2.47. How to know this three scale factor? We use this equation. We use this equation and we generalize this. We already know for example, we need to know the top displacement. Top displacement should be, for the different mode shape, should be equal to 1.0. So we can add together. But for the first story is the 3D, the third DOF. We know that in this mode shape is equal to 0.3 minus 676 to 0.747. So this is the number 3 DOF, number 3 knot, or we call it knot 3, knot number 3, the mode shape. For example, this is the first mode, second mode, and the third mode. These three values here, so we can put back to the mode shape calculation. So this mode is means the displacement for each node. For the third node, it should be this three value. For the second, fourth, should use this three value to multiple each theory result data from the curve, the previous curve like this one. So we can finally use the Excel table to compute each time step. We can get the final result. So we can have the conclusion for the calculation of the model supervision method. At the very beginning, we need to know the systems, MDOF systems, stiffness matrix, mass matrix, and of course the damping ratio. And then we can compute the model. After the model analysis, we know that the circular frequency of different mode and the period of different mode and the mode shape match, and this one's very key important. And then we use this with this mode shape matrix and the mass. This is the original mass and the mode shape matrix. We can compute the generalized matrix. So we use the star, and then we can compute the external loading factor for the each mode shape. This is generalized external loading factor, and we can use the basic equation to transfer to be each DOF, each mode. For example, mode I. This is mode I. We can have the basic equation for the different mode. We know each key element for the basic equation, like the mass, damping constant, stiffness, external load or the acceleration factor. And then we use Duhamel integration method or the Lumark beta integration with theta, and there's so many different methods for the single degree of freedom calculation. And then we can get the whole time history data of the result of the displacement for the each mode, like a mode 1, mode 2, mode 3. And we can use different mode shape factor to compute the real time displacement for each time step. And this step we also call the mode supervision method. So in this one we can use the Excel table or the computer program to generate the final whole result for the time history. So this is the calculation method. It's quite easy to understand supervision. What the meaning of the supervision is to add up 3 modes result together. And then this is the result we capture from compute from the model supervision method. And then we get this result, we only get the displacement result. And this is the key result, the original result from the calculation. And then we need to know the shear, like a storage shear. And after get the storage shear, we can know each column shear. So this is internal force result. How to compute the internal force result is quite easy for the story model. And because we already know each node time history data from the result, we can use the computer or the program to generate each time step, the result of the time step. We know the exactly displacement to each story, and then we can use the different the calculation to capture the different displacement for the each story. We call it the internal story displacement or internal story drift. And then, for example, the third story is U1 minus U2. In this story is U2 minus U3. In this story is U3 only minus 0. And this is internal story displacement. And we know that we already know each floor. For this one is K1, K2, K3. This is the story stiffness. So story stiffness by the, for example, this one U1 minus U2, or we call the theta 1. This one we call it the story internal story displacement. We can use stiffness by the displacement equal to the internal shear. We call it V. So this is compute the V1. So we can get the V1, V2, and V3. This is the story shear. So we can use this method to capture the story shear. This is the result, the T equal to 6 for example. The result, the internal shear and internal overturning moment. Moment is quite easy. After we capture each node shear, we can compute the relationship between the story floor height and the story shear. We can capture the overturning moment. OTM means overturning moment. So in the detailed calculation, you can see the teacher's note. They have the detailed calculation for the story shear and the overturning moment. And this is, you should know how to capture the story shear and the overturning moment. So, and this is the whole content of the PowerPoint. And in the note, I have some additional knowledge to teach you. So we transfer to the teacher's note. So come to the special note for the MDOF system calculation. And this is the detailed calculation of the mode supervision calculation. And you can see that this is the calculation of the exactly moment of this second 2.56 second calculation. We can capture two of the different mode time history result of the displacement. We know that in mode 1 the displacement is 3.8 millimeter, y2 is 0.5 millimeter, and y3 is 0.02 millimeter. So this is the result for the exactly moment at the 2.56 second. And then in the mode shape, we capture the third DOF displacement. So we use the phi of the third DOF, like first mode is 0.300. This is non-unit value. And this is the second mode and the third mode. We use the supervision equation to add up together. We capture the exactly movement of the displacement in 2.56 seconds is 0.85 millimeter. And this is the detailed calculation of the displacement. So if we need to capture all the time history data of the displacement, each time step you need to calculate by this equation. Okay, we can see the next page. This is the detailed calculation of the story displacement of each story, and we use the stiffness by the displacement. We can capture the shear of the story shear. And story drift, what is drift? Drift means the story difference displacement, the difference between two story displacement over the story height. And this is the calculation of the story drift, because the story drift always had the limit. For example, for frame structure, sometimes the story drift should less than like a 500, 1/500, and this is the story drift limit. So we need to know how to compute the story drift limit. And the other point is how to measure the time history data. Time history data, we want to focus on the absolute maximum value. For this one is the positive maximum value. This one is negative maximum value. But the absolute value is need to get the maximum value for the absolute value. So in this time history or 1940 EL Central earthquake record, we capture the maximum absolute value is 0.357 G, and this is the exactly record of the EL Central earthquake ground motion. And if we in the calculation, sometimes we need to transfer this record to be a certain maximum acceleration record. We need to scale up or scale down. For example, the target acceleration p-value in the some calculation, for example, for the code for severe earthquake, usually for severe earthquake for 7-degree zone, the alpha max, the maximum acceleration to be 220 gal. 1 gal means 1 cm per second square, or equal to 2200 mm per second square. So this is the target value, and we need to scale up. For example, in this record, the maximum value is 0.357, so we need to scale up to be 220. So this is the scale factor. So for the Chinese code, for example, the grade 7 earthquake, the frequency earthquake means very small earthquake, is 55. This is for the normal concrete design loading. And the moderate earthquake is 2 times of the frequency earthquake, so it's 110 gal. And the severe earthquake is the double of the moderate, is 220 gal. And this is the severe earthquake. So this is 3-level design for the Chinese building design code. In the next page, we will introduce how to use another method to compute the maximum deformation or displacement of the result. And we know that we in this calculation, we capture all the time history and we get the maximum value. We found that the maximum acceleration it happened on the 6.8 second. So we captured this second. We were and for each, for example, for each record we can capture the maximum acceleration for each mole. For example, the mole 1, the maximum displacement is 79 mm displacement in maximum value. When will happen in the 6.08 second will happen the maximum value, and the second mole the maximum value happen on the 2.24 second. The value is 25.7. So for each mole we can capture the maximum value in the different happen on different time, but the maximum value, because when we get the whole time history result, we can need to use Excel table or computer program to get the whole record. But sometimes for the easy hand cal, maybe we can use the maximum value for each mode, the maximum time history value for each mode, and then we can use some simple addition method to compute the reference maximum value for the result time history. For example, we can use simple addition method. We can use 3 mode maximum value like 79, 25.7, and 1.67. These 3 mode. For the top displacement, the mole shape factor is 1.0, 1.0, and 1.0. So the top displacement, the maximum value is 1.637. But you know that in there happen the maximum value, the time is different. So we use this method to be close to the accurate result. The accurate result of the time history is in this calculation. The exact time is 6.04, and the actual value, the actual maximum value for the final time history is 82. But we use simply addition method. It also called simplified maximum envelope of the each mole. The additional method, we can compute the maximum value is 106 millimeter. Should be always larger than the exactly value. And this is the calculation method. This is the tolerance of the calculation method. But so always we don't use this method. So we transfer to use another method called SRSS. It means the square of the summary of the square root. The square root of the summary of the square. So we can use each values square, add together, and have the square root. So the result is much more closer than the simple additional method. So this one is quite near to the exactly value when we use the whole time history calculation. So this is what we mean to use SRSS, square root of the summary of the square. Okay, the next one, if we don't have time to calculate like a time history, we can also use spectrum to compute the maximum displacement. For example, when we have a time record, we can transfer to be the displacement spectrum like this shape. And for the spectrum, we know that when we know the period, we can capture the maximum displacement for this period. For example, for this 3 DOF system, we can have 3 single DOF system, and then we capture 3 different mode and different period. For each period, we can capture the maximum displacement by using this spectrum method. This one we already learned in the lecture 4, the single degree of freedom calculation. And then we apply the load factor into this calculation, because we need to multiply by these 2 things, the result multiple by the load factor, because the load increased, so the result should be increased in the same proportion. So we combine and we have a multiple value and equal to the reference displacement for each mole, and then we use SRSS method to compute the preference maximum displacement for the final result. So this one is so close to be the exact value. So this one we also call the spectrum SRSS method. It's quite useful when you get this record. In this record, we just use Duhamel integration. So to compare different method, we can use the Duhamel integration before we run the model analysis. This is the spectrum method. We also call the spectrum method. Okay, so here we introduce two more simplified method compared to the spectrum method. One is the equivalent lateral force method. You use the mode shape to determine the story force by the mode shape factor. And at the very beginning, we know that after we have a model analysis, we can capture the different mode and different period and the mode shape. And after that, we can use Duhamel integration. After we get the ground motion, we can generate the acceleration spectrum. And for different mode, we can find the different maximum acceleration. And if we run the mode shape analysis, we can capture 3 mode shape. We assume the lateral force follow the mode shape. So we can use this equation to compute each story force by using the mode shape. The mode shape compared to the 3 elements. One is m, and m is the mass of each story. A is the mode of mode acceleration we can capture by use spectrum method in this diagram. And phi is the mode shape factor for each mode. R is using this value of the loading factor of the mode shape. We can capture by using the loading factor we described before, using the generalized loading factor over the generalized mass for each mode. And you can come back to the previous page. And after we use this calculation equation, we can capture each value of different mode and the different story. And then we can use, this is the external force as a P load of each floor. Then we can use 2 different force external load to compute the story shear force. And then we can use SRSS method to compute the exactly shear force by using SRSS method. And this is the simplified method result. We can compare to the exact result by using the mode supervision method. So we can see that it's close, but it's not exactly the same. So we also call this one is simplified method. But this is using the model analysis. We also need to use model analysis. So we need sometimes to run the model analysis, this simplified method. But in the next page, we totally don't need any model analysis. We just need to compute the base fundamental period and use the spectrum method to capture the acceleration by this fundamental period. This is, you can use equation to compute, or use the lump sum mass or lump sum stiffness to compute the fundamental period. Then one structure had only one fundamental period, so we use one period to compute the acceleration. And because we know the total mass, we can use these 2 equations to compute the total shear, or it's also called the base shear. How to transfer to the base shear to each story shear? We're using the mode shape factor also, but if we don't know the mode shape, we can assume the mode shape follow the straight line. So we have the relationship of the mode shape to compared to the floor height. So we can know that for this one, if we assume the top is 1.0 and the second floor, because the floor height is equal, so we can know that it's 0.667. This is simplified method. If the story height is different, the value will change, but this one is related to the story height only. And then we will Note that the external force, it follow the shape is linear as the story related to the story height, and then we will compute the equation related to A and F, and then we add up these three story external force, we will get the final base shear. Because base shear, we already used this method to compute as 229. So we just compute the AF equal to something, and we'll put back this AF back to the calculation. We know that each floor had the certain value of the external shear, external force, and then we can compute the internal story shear, and then we can use SRSS method, and this is the result of the base shear method. We can compare to the SRSS result based on the model analysis and the exactly time history. This is the exact result of the calculation. We have found that it's close, but it's more and more a lot of error of the calculation. So this method is just for the simplified adjustment for the structure. It's not an accurate calculation method. So that's what this base shear method come from. It also need you to find out the mode shape, but we just assume the mode shape is a linear, it's like a straight line. Actually, sometimes the mode shape is quite like a parabolic curve, but we just want you to assume the first mode is equal to the straight line. So there will happen a lot of error inside. So this is a simple calculation of the base shear method. In the next lecture, Rachel will introduce more and more calculation method for the MDOF system. So you can compare to the base shear method we introduced here. Okay, thank you for listening the PowerPoint. If you have any question, you can submit the question to the Moodle system. Thank you. Bye-bye.